Okay, good morning. Yesterday we looked at three-phase power, how the three-phase power can be calculated, especially in a balanced system, which is either connected in star or delta format. So we'll be looking at how to measure the power in today's class. So let me start by first of all looking at different methods of measuring power. I'm sure all of you must have seen the energy meter that is existing at home from where the electricity reading is taken. So energy meter generally measures the amount of kilowatt hour, that is the energy measured in kilowatt hour, amount of kilowatt hour consumed at home. So this is what is being measured. So this is essentially watts. How much is the watts multiplied by how many hours that we have consumed, what amount of watts, that divided by 1000. This is what is actually specified or displayed by the meter, energy meter that we have at home. Instead, if I want to measure the power is generally measured in watts, and that is generally done by looking at how much is the voltage and how much is the current and what kind of displacement, the phase displacement happens between voltage and current. So what is the kind of displacement that is there between voltage and current? So that is actually going to give us the power measurement exactly. Okay. So for this, generally there are two types of instruments that are used. One is called electrodynamometer, wattmeter, and the other one that is normally used in AC circuits particularly is induction type wattmeter. These are the two types of wattmeter that are used very commonly in many of the systems. Electrodynamometer wattmeter can work in both DC as well as AC, whereas this will work only in AC. I would like you guys to look into, the internet and study about these things, but I'll just give you a rough idea as to how these two work. I want you guys to do some homework. So please study this on your own. You try to look up, okay? And so this is for self-study. I'm talking about this for self-study. So let me write this as self-study. I want you guys to study on your own. Okay. So what happens in an induction type wattmeter generally, especially which is used for AC system, is if I am having a load which is supplied with an AC supply. So I'm going to just have an AC supply connected to a load, and I want to measure what is the kind of power it is consuming. I will have basically two magnets. One of the magnets will be supplied with the voltage what is coming up here. So let us say this is going to be supplied to one of the magnets, and I'm going to have one more magnet which is connected in series, which is going to exactly carry whatever is the load current, and that is also connected to the load. So this is the shunt magnet, or we call this as the voltage coil. You may say voltage coil, which is actually wound around an electromagnet or a iron core. This is the series magnet, which is also generally specified as the current coil. So you are going to have current coil or the series magnet, which is actually carrying the current, which is same as the load current. The other one is going to be shunt magnet or the voltage coil. Now, these two actually will create their own magnetic field. And because they create their own magnetic field, there will be a small aluminum disc which will be mounted in between these two. So this will have induction because of the current coil's magnetism as well as voltage coil's magnetism. Both of them are going to interact with each other, due to which this is actually going to deflect by certain angle. Depending upon what kind of force it is experiencing, it is going to deflect by certain angle. And the pointer would be attached to this. So that is the reason why the pointer should deflect as per the induction that is taking place from the voltage coil as well as current coil. So this wattmeter disc actually indicates the force generated because of the interaction between the voltage and current. Both of them are going to interact with each other. The voltage is voltage across the load and current is current through the load. So overall, the force that is actually manifested by the deflection, by means of a deflection, that is going to be proportional to the power, because the force that is generated actually does the mechanical work ultimately, because of which what you get as the deflection will be the real power. So this is what is the basic working principle of this induction type wattmeter. Okay, so I would request you to definitely study a little bit about this so that you get familiarized with some of the measuring instruments as well. I think it's important to know about some of the measuring instruments. Okay, so now that we know that wattmeter can be used for measuring power, let us try to see how power measurement is done in a three-phase circuit. So how power measurement is done, we are going to see. The first case that I'm going to take is three-phase, four-wire, star-connected system with balanced load. What I mean is, we are going to have balanced source as well as balanced load. I'm specifically mentioning balanced load because I am talking about three-phase, four-wire, Y-connected balanced supply with balanced load. So in which case, I am going to have the three-phase supply somewhat like this. So I'm going to have this as A phase and this as B phase. So I'm going to have B phase connected from here and I'm going to have C phase connected like this. All three phases are balanced and I'm going to have the neutral here and I'm going to have the three-phase load which is also balanced connected somewhat like this. So this is how they are connected. Okay, so if I call this as VAN and I call this as VBN and this as VCN, now this is connected here and these two are connected together and I'm going to connect this to this point. Okay, so let me call this as Z. And I'm not even specifying ZA, ZB, ZC because I'm assuming all three of them are equal to each other, which means whether I connect this neutral to this neutral or not, it doesn't matter because I'm not going to have any current between the two neutrals. IA plus IB plus IC is very much going to be equal to 0 because I'm assuming balance load and balance source. So between N and N, there is no current. There is no current whatsoever. Now all I need to do is to connect the wattmeter between maybe one of the phases. The current coil has to be connected here. So let me probably erase this and let me show as though I'm going to connect the current coil here. So current coil of the wattmeter I'm connecting here. And when I'm talking about the potential coil, which is actually the shunt coil, this is the series coil or current coil. Okay. This will be like an ammeter, normal ammeter, what you use for measuring the current. So this will always come in series. And whenever you connect something in series, it will have very, very small resistance so that it doesn't distort the actual current that is flowing through the circuit. If this had a higher resistance, obviously it will intervene with whatever current this particular phase is carrying. So you don't want this current to be manipulated, or it should not be changed. So that is the reason why normally you are going to have a current coil having really small resistance. Whereas when I talk about shunt coil or potential coil or voltage coil, if I may call that a shunt coil. So series coil is the current coil, and shunt coil, the shunt coil, you can call that as either voltage coil, which is very similar to a voltmeter, which will have extremely large resistance. So it will not carry any current again. It will carry hardly any current, whereas series coil will have hardly any voltage drop. Okay, so this voltage coil, or I can call this as potential coil. Sometimes this is also specified as pressure coil. So we can call it by one of these three names. So the shunt coil is shown as a high resistance because it will hardly carry any current that can be directly connected to the neutral point. So either neutral of the source or neutral of the load. Either side is fine. So I'm connecting it to the neutral. Now what comes here will be the per phase voltage. So in this particular case, the shunt coil is, if I may call this as some C and this is V. So CV is the potential coil and this is going to carry only per phase voltage. Okay, and I'm going to have this shunt series coil, which is the current coil. Current coil, let me call this as some, this generally is connected to the mains or the supply, and this side is connected to the load. So generally, if you look at the wattmeter, you will see four terminals, M, L, C and V. Any wattmeter will have M, which is actually going to the mains, L, which goes to the load. So these are the two terminals of the current coil. So ML is the terminals of the current coil. These are the terminals of the current coil. So this will carry one phase current. One phase current. Okay. So I am going to have M and L as the terminals of the current coil, and C, or sometimes we will call it as common terminal, which is the common terminal between the current coil and the voltage coil. So this is the common terminal. Generally we call this as common terminal, COM. So C and V, this is the voltage which is actually connected to the reference point. So this will be the voltage reference point, and common will be the common point between the current coil and the voltage coil. So this CV carries per phase voltage and ML carries one phase current. So basically what it is going to read is VI cos phi, which is the real power, which is actually going to be the deflection that comes because of the force developed. Okay, it is going to create a deflection because of the force experienced by the pointer or the disc, whatever is attached to the pointer. So I would say that this, what it sees, actually it will be able to deflect as per the force instantaneously faced by this particular disc. But because the disk has an inertia, there is an inertia, it will ultimately rest at a particular position which is corresponding to the average power. Otherwise, if you apply a very, very low frequency supply, instantaneous power would also vary at extremely low frequency. So you may be able to see the pointer oscillating normally in the wattmeter. But when you have 50 hertz supply, because of the inertia of the system, and the power is going to vary at twice the frequency. We drew this earlier also. It will vary at twice the frequency. That is the reason why you are going to see that ultimately the pointer rests at a particular position. So the pointer will always indicate the average power. The average power is indicated by the pointer. So when the average power is indicated by the pointer, that is going to be Vi cos phi, which is going to be P per phase power. So this is going to be per phase power, which is P. And if I assume that it is a balanced load, I'm going to have 3-phase power will be equal to 3 times the wattmeter reading. Whatever you are getting in the wattmeter, if you multiply that by 3 times, that is going to give you the 3-phase power, which will be 3P. So this is possible to do. This kind of measurement is possible to do only if I have the neutral present. And it should be a star connected system and it should be a balanced load. So single wattmeter method, this is called generally single wattmeter method. So I can say single wattmeter method of power measurement can be implemented, or it is possible only in 3-phase 4-wire star connected system with balanced source and balanced load. Generally, what is available from the grid is a balanced source. It will not be unbalanced. So the load being balanced, that is absolutely in the hands of the person who is using this supply. So that is not going to be in the power systems or power grid's hands. It's going to be in the hands of the consumer. So only if I have a balanced source and balanced load, I would be able to use a single wattmeter method. Okay, so this particular method is generally known as the single wattmeter method of power measurement. There is one more method called 2 wattmeter method. So you can use 2 wattmeters to measure the power in the 3-phase system. So let us try to take a look at how the 2 wattmeter method works. So let us say I'm going to have A phase supply here and B phase supply here and C phase supply here. Okay. Now I am again assuming a star connected supply, but only with 3 wires, not the 4th wire. So it can very well be delta connected also, because I am relying only on the presence of 3 wires, not 4 wires. Okay. Now let us say I'm going to have again a star connected load. I'm just assuming that the load is a balanced load or unbalanced load. It doesn't matter. So I'm going to have 3 loads connected. And I don't know whether it is resistive or RL or RC or RLC. I don't know. So I'm just putting them as generalized loads. So I'm going to have ZA here, ZB here, and ZC here. 3 voltages. Okay. Now I'm going to connect one of the current coil. The current coil is indicated like this. And I'm going to have the current coil of another wattmeter like this. Okay. So let me call this point as, like I told you, M and L. So let me call this as M1 and this is going to be L1. And similarly, this is going to be M2 and I'm going to call this as L2. Okay. Now I'm going to connect the 3rd phase directly to the load, but I'm going to have from here the pressure coil or the potential coil that is connected between A and B. And similarly, this potential coil is also connected somewhat like this. So this is going to be the pressure coil. This is going to be current coil. So let me write this as current coil of wattmeter 1. And this is the common point that I'm going to have. And this is the V1 point. And this is going to be again common point. And this is going to be V2 point. Okay. So this corresponds to this entire thing corresponds to wattmeter 1. So let me write this as wattmeter 1. And this is going to be wattmeter 2. So these are the 2 wattmeters that I have got. This is wattmeter 1 and this is wattmeter 2. And now if I am trying to look at what is the current that is coming through wattmeter 1 and what is the voltage that is coming through wattmeter 1. So I can say wattmeter 1 is going to have, if I say this is IA and this is going to be IB. Please note I am writing lowercase letters, which means instantaneous current, and this is going to be IC. I should write this as VAB multiplied by IA. That is what is coming across wattmeter 1. And wattmeter 2 is going to read, please note that it's measuring the voltage of C with respect to B. So I have to write this as VCB multiplied by IC. Okay. Now if I try to look at what is W1 plus W2, I should be able to write this as VAB multiplied by IA plus VCB multiplied by IC. This is what I'm going to get. So I should be able to write this as VA minus VB multiplied by IA plus VC minus VB multiplied by IC. Okay. Now I can write this as VAIA plus VCIC minus VB multiplied by IA plus IC. Okay. Please note this is Kirchhoff's current law. If I have to follow IA plus IB plus IC, it cannot go anywhere. There is no way it can flow anywhere. So I have to have in a 3-phase 3-wire system, no matter what, I have to have IA plus IB plus IC equal to 0. It cannot be anything else. It has to be this way when I look at the load terminal. So I can say IA plus IB equal to, rather IA plus IC equal to minus IB. Whether I like it or not, this has to be valid. There is no other way. So I can write this as equal to VAIA plus VCIC, and IA plus IC is minus IB. So I can write this as VBIB. So this actually gives me directly 3-phase instantaneous power. This is the instantaneous power in A phase. This is the instantaneous power in C phase. And this is the instantaneous power in B phase. So this is actually the instantaneous power or the total instantaneous power in all the 3 phases put together. So this is going to be the summation of all the 3-phase powers, instantaneous powers, when I am summing up the wattmeter readings of W1 and W2. So this will be valid no matter what, whether the load is unbalanced or balanced, because IA plus IB plus IC equal to 0 has to be valid here because of the Kirchhoff's current law. I can't help but agree with this. This has to be definitely valid. So 3-phase 2-wattmeter method generally will be valid for, this is 3-wire system. We are talking about only for 3-wire system. This should be valid for balanced as well as unbalanced loads. That I can say from the above expression, basically. This will be valid for both. Absolutely. We have taken star connected load and star connected supply. I would request you to do it for a delta connected load. So I am again giving you something as homework. So I am asking you to see whether it works for delta connected system. So for the delta connected system also, I should be getting ultimately the three-phase currents instantaneously. That is VA, IA, VB, IB and VC, IC, whether I'm getting at all or not. I want you to check it out. So please prove this for delta connected load. I want you to prove this for delta connected load. Now, let me try to take the 2 wattmeter method a little more carefully so that whether I would be able to infer the power factor. So, can we deduce the power factor of the load in 2 wattmeter method if the load is balanced? So will I be able to determine whether I will be able to, whether I will be able to determine the power factor angle or power factor using 2 wattmeter method, especially if the load is balanced. So let me redraw the circuit diagram what we had done. So I'm going to have A phase, B phase and C phase supply here. These are the 3-phase supplies. So this is VAN, this is going to be VBN and this is going to be VCN. And I'm going to have the 3 loads. I can show it in star connected format, something like this also. Doesn't matter, but they are going to be balanced loads. Okay, so all of them are going to be completely balanced. Maybe I can take this as some R plus JX. This is also some R plus JX. And this is also plus some R plus JX. So plus I'm writing, which means it is reactive. So I'm taking 3-phase loads like this. So now I'm going to connect 1 wattmeter here. This is the current coil 1. And the second one is the pressure coil. So the potential coil is going to be connected between A line and B line. The same way I'm going to have on one side, I'm going to have current coil 1. On the other side, I'm going to have a current coil 2. And this is going to be connected here. The same way this will be connected here. So this is pressure coil 2 and this is potential coil 1. So I'm going to call this as wattmeter 1 and I'm going to call this as wattmeter 2. So these are the 2 wattmeters. So we wrote this already. Nevertheless, let me write it again. So wattmeter 1 is going to have whatever is the voltage, that is the voltage between in the pressure coil in wattmeter 1 is VAB and the current that is flowing is IA. So if I write it in terms of the wattmeter reading, it is going to sense the average power. So let me write VAB, whatever is the RMS value probably, and IA, which is going to be the RMS value. And I have to say cosine of angle between VAB and IA. This is what we said, as the force will be developed between the voltage that is being applied and the current that is being applied to the current voltage coil and current coils respectively. And whatever is the angle between them, that is going to play a vital role in deciding how much is the force that is being developed. So that is the reason why I am writing like this. Okay. And as far as W2 goes, I will have VCB multiplied by IC multiplied by cosine of angle between VCB and IC. Right? So let us try to draw a phasor diagram and then see what is the angle between these two. Okay. So let me try to draw the phasor diagram right here. So let's say I am going to have my VA like this. Okay. And VB will be 120 degrees shifted, but will be having the same magnitude. So let me write VB like this. And I'm going to write VC like this. So this is going to be VC. So VA and VB and VC I have drawn. And please remember, VA magnitude is same as VB magnitude, which is same as VC magnitude, which is V phase. That's what we say. This is the per phase voltage. And we already derived in a star connected system, √3 times the per phase voltage will be line voltage. Now what I want is VAB and VCB. So before that, let me draw the currents. If I have assumed that R plus JX is the impedance, which is inductor. So obviously I will have IA lagging behind. So this will be IA and this will be the phase angle. And I'm talking about all the three phases having balanced load. So the current should be exactly the same and they should also have the same phase angle. So I should have essentially the current here somewhat like this. So this will be IB, which will have phase angle phi. I'm sorry, I should have written capital IB. So I'm going to write capital IB. I am writing everything in terms of say RMS values. And I'm going to have IC, which is again having capital IC as the value, and it will lag behind by an angle phi. So all three phases will have the same power factor angle and all of them are going to have the same value of current, IA, IB, IC respectively. Okay. Now let me try to draw what is VAB and VCB. So let me take this along here. So this is going to be actually minus VB. So I'm going to have this as minus VB. Okay. So let me draw the length properly. So this is going to be minus VB. Now, if I want VAB, I have to just complete this parallelogram. And similarly, if I want CB, again, I have to complete this parallelogram. So this is how I have to complete it. Okay. Now, if I try to look at what is the value of VAB, this is going to be VAB. We said that this is √3 times VA or whatever that we already said. But this angle will be 30 degrees because this entire thing is 60 degrees and this will come in the middle basically. The same way, if I try to draw where my VCB is, so VCB is going to be drawn like this. So this is going to be VCB and I will have again, if I try to look at it, it will have 30 degrees on this side and I'm going to have 30 degrees on the other side as well. Okay. So now let us try to see what is the angle between VAB and IA. VAB is here 30 and IA is 5. So I'm going to have 30 plus 5 as the angle here. And let me look at this VCB. So this angle is 30 and this is phi. So 30 minus phi will be the angle here between these two. This is going to be 30 minus phi. So I should write this angle, whatever I have got here, as 30 minus phi. So I should write this angle as 30 minus phi. So I should be able to write this as W1 equal to VAB multiplied by IA cos of 30 plus phi. Okay. And W2 will be equal to CB multiplied by IC and cos of 30 minus phi. If it had been leading power factor, it might have been the other way around. For W1, I might have got 30 minus phi, and for W2, I might have got 30 plus phi. So I want you guys to definitely do it for leading power factor. Again, I'm adding one more homework. Please do it for leading power factor. Please draw this diagram for leading power factor current. So I want you to do that. Please try to do that so that your understanding becomes stronger. I want you to do this. Okay. So let us first of all finish with this. So we said overall power previously what we derived was W1 plus W2. So let us try to calculate what is W1 plus W2. That is going to be VAB, which is the line RMS value, IA or IC, which will be the line current value. Okay, multiplied by cos of 30 plus phi and cos of 30 minus phi. They have to be added. So I should say cos 30 plus phi plus cos 30 minus phi. So this is cos C plus cos D, which will give me cos C plus D by, is it cos sine C plus D by 2 and sine C minus D by 2, whatever. So that is the way it should be, right? So I should have, let me otherwise write cos A cos B minus sine A sine B. Let me write that. That is easier. So this is going to be cos 30 cos phi minus sine 30 sine phi. And cos of 30 minus phi is going to be cos 30 cos phi plus sine 30 sine phi. I can write it like this. So which means these will get cancelled. So I have only cos 30 cos phi, which will be root 3 by 2 and root 3 by 2. So I'm going to have root 3 VL IL cos phi, which we derived in the last class, saying that that is what will give you whether it is delta connection or star connection. We said root 3 VL IL cos phi will give you 3-phase power. So this gives me the total 3-phase power. This is going to give me the total 3-phase power. Okay. Now rather than doing W1 plus W2, obviously from this expression I would be able to say I will get sine phi in the expression if I subtract W1 and W2. So if I say W1 minus W2, I'm going to have VL. So I'm going to have VL IL sine phi and sine 30 twice. This is going to be 2 times because sine phi and sine 30, that is going to be added together. So this is what it is. And sine 30 and 2 will get cancelled with each other, right? Sine 30 is half. So I'm going to get VL IL sine phi. Okay. Only difference is if I want to do sine phi by cos phi, I will have to divide W1 minus W2 divided by W1 plus W2, but there will be a root 3 factor. So if I say root 3 times W1 minus W2 divided by W1 plus W2, that is going to give me sine phi divided by cos phi, because I would have had root 3 VL IL on the top and I would have had root 3 VL IL at the bottom as well. So I can cancel this root 3 VL IL and this. So I will be able to get tan phi. So the phase angular shift between the two the two quantities in every phase, that is the voltage and current in every phase, that can be obtained if I just do the 2 wattmeter method of power measurement. That will actually give me tan inverse of root 3 times W1 minus W2 divided by W1 plus W2 will give me phase angle phi between voltage and current. So this is going to exactly give me the phase angle between the voltage and current, from which I should be able to deduce what is the power factor of the load without really going into the details of, the actual voltage and current being measured and the phase shift between them being looked into. Without that, I would be able to get what is the power factor. Is this clear? Any questions on this? Any questions? Any questions? In fact, in a three-phase, three-wire system, how can we do reactive power measurement? Just using single wattmeter, we should be able to do reactive power measurement. This is using single wattmeter, and if it is a balanced system. We should be able to do reactive power measurement directly. So let us see again. Let's say I have this as the A phase voltage, this as the B phase voltage, and this as the C phase voltage. So these are the three phase voltages. Okay. Now I'm going to have, let's say, a wattmeter. The wattmeter actually will have one current coil and one pressure coil. So let me just show the current coil here. And that is connected to the load. So I'm going to have the load here, the load here, and the load here. Okay. So I'm going to complete this. So this is the current coil. So let me call this as M and L. Only one wattmeter I'm going to use. Now there is pressure coil which is sitting here. So I'm going to connect the pressure coil actually between the other two phases. So what I'm going to do is I'm going to connect this here and I'm going to connect this here. Okay. So I'm connecting it as VBC. If I may say, this is the common point. So let me write, this is common. Right now, this is not common. Please note, I have disconnected M from common. I cannot really connect it like that. Otherwise, I'll be short circuiting A phase voltage with that of B phase voltage if I try to connect it like this. So I cannot connect it like that. So common and M are not connected in this. M and common are not connected in this diagram. Okay. So this is the other point, which is V. So I have got on one side IA and I have got VBC. This is what I have given to the wattmeter. Okay, this is what I have given to the wattmeter. So let's try to now again draw the phasor diagram. So this is, let me draw it again. This is going to be VA. This is going to be VB. And this is going to be VC. Okay. Now, if I try to look at what is VBC, so C comes here. Okay. So if I try to look at, this is minus VC. And I'm going to say maybe my current is lying somewhere here. So this is IA. And this angle is phi. Okay. Now I'm going to have VCB somewhat like this. So I have to draw the summation of these two. So this will come out to be somewhere here. This will be VBC. This is going to be VBC. And VBC and VA they are shifted from each other by 90 degrees because this will be 30 clearly. I have not drawn it very well. This is also 30. So obviously I'm going to have this entire thing is 120. Between VA and VB, it is 120. This is 120 and this is going to be 240. If I try to look at the entire thing, this will be 240. So obviously I'm going to have this as 120. 120 minus 30, this will be 90. So this will be 90 degrees. If I try to write what is the phase difference between VA and VBC, it will be 90 degrees. So between VBC and IA, the phase shift is 90 minus phi. Am I right? That is going to be 90 minus phi because this entire thing is 90 and this is phi. So I am looking at the phase shift between IA and VBC. So this is going to be 90 minus phi. This is going to be the phase shift. So I can write basically the wattmeter, if I may call this entire thing as the wattmeter. So this is W. So reading in W will give me VBC multiplied by IA multiplied by cos of 90 minus phi, which I can write as VL IL sin phi. So this is going to be VL IL sin phi. Okay. If the current had been leading, what I would get will be cos of 90 plus phi, not cos of 90 minus phi. Cos of 90 minus phi sin phi, this will be positive. But if it had been cos of 90 plus phi, it will be minus sin phi, right? So if it is minus sin phi, please note many of the times in wattmeter, if you look at the complete readings, it will start from 0 and maybe it will be up till 750 watts or 1500 watts. So it will have deflection maybe only on the positive side. So if this is the pointer, the pointer will essentially indicate somewhere here, or it may go within this 1500 watt range. Now, if it is minus, if it is going to show minus, then you would see that the wattmeter reading will be kicking back. That is, it will actually go beneath 0. So we will call this as wattmeter reading, wattmeter pointer is kicking back. If it is kicking back, if one of them is completely reversed, either the potential coil is reversed or the current coil is reversed. So you have to turn off the power supply from the entire system, either reverse the current coil. So if I may call this as M and L, L should be connected here and M should be connected on the other side. So I would connect it in such a manner that this is VAN, and I'm going to connect, if I may say, this is the wattmeter. Now I'm going to connect it here and connect this here. So this was my M and this was my L. L has been now connected towards the supply and M has been connected towards the load. But the potential coil should be allowed to remain the same way. So either I reverse the potential or I reverse the current coil. One of them has to be reversed, in which case whatever is kicking back, it will come back to its original position. So if I am using the sin phi measurement or the reactive power measurement, in that case, if it is kicking back, you can say it is probably a capacitive load. If it is not kicking back, it can be inductive load. So that will actually distinguish between the two types of power factor. So if I am looking at this, this is the reading in the wattmeter, which will be VL IL sin phi. So I should say √3 times reading in W will give me the three-phase reactive power. So the three-phase reactive power you will be able to get just with one single wattmeter, provided it is a balanced system. Only if it is a balanced system, we will be able to get the reactive power also measured correctly in a balanced system by using only one single wattmeter, provided I connect the current coil in one phase and the potential coil across the other two phases. Okay, so this is essentially about the three-phase system. We had seen in the three-phase system starting with the generation of three-phase voltages. So we started with generation of three-phase voltages, and after that we looked at star or delta connection. We also talked about advantages of three-phase voltages over single-phase voltage. Then we talked about star and delta connection. And we also talked about the relationship between the phase voltage and line voltage and phase current and line currents in star and delta connection. And we also looked at the power measurement, power expression we derived, which is actually √3 VL IL cos phi. I would like to emphasize that any three-phase equipment will always mention what is VL and what is IL. It will never mention the phase values. It will always mention only the line values, RMS values. So any three-phase equipment mentions only VL, IL, RMS values. So if you have a 400 volts, 15 ampere induction motor, three-phase induction motor, it specifies 400 volts is the line voltage and 15 ampere is the line current. It is going to always mention line voltage and line current. Okay. So based on that, we got the power expression. Then we looked at power measurement in three-phase system using single watt meter, using 2 watt meter. Then we expanded the 2 watt meter method also to look at the power factor, deducing the power factor, and finally we concluded with reactive power measurement. So in the coming tutorial class, we'll be doing some problems on the three-phase system.